Hello everyone. Looks like we're live here and time to do our lecture on minimum spanning trees. And this is going to be one of the lectures that's important for Project 4. So the big ones for Project 4 are this one, and Project 4 comes out tomorrow, so you'll be ready for Part A of Project 4. And then the other two parts, I was just looking to see when we do that. Okay, so Thursday is going to be the other big part, the traveling salesperson problem. So you'll have enough after today. When Project 4 comes out tomorrow, you'll have everything you need to start Part A. Part B is going to be a traveling salesperson problem heuristic. So you can start looking that up, if you're not busy enough with Part A. So Part A is going to be MST. Part B is going to be, we call it FAST TSP. And what you can do is go do a Google search for TSP heuristics. That is not the most neat handwriting. I guess I could be a doctor. I am a doctor. That's awesome. So TSP heuristics is Part B, and then Part C, which we call Opt TSP or Optimal TSP, is going to be on Thursday's lecture. So let's get going on the MST today. So minimum spanning trees are a graph problem. And so if I gave you an edge-weighted undirected graph with vertices and edges, you want to find a subgraph that has the same vertices but a new set of edges E prime. We're going to choose E prime, our subset of E, such that all vertices are pairwise connected. What that means is that we have to end up with a connected graph. We can't have a disconnected graph. And the other thing is that we want the sum of all edge weights in T to be minimum. And T here and the tree should tell you, hey, we're trying to make a tree out of our graph. So if there's a cycle in it, then we should remove an edge from the cycle, and we remove the one that has the highest weight because we're trying to get to the smallest possible weight. So T really must be a tree. There must be no cycles in the graph, because if there was a cycle, that would be an extra edge. It would no longer be minimal. It might be connected, but it would no longer be minimal. So we can get rid of one of those edges in the cycle, and we choose to get rid of the edge with the highest weight. Now, one way we might use this algorithm is to solve a problem of connecting data centers. So this is some data. You can look at the link down there of actual data centers across the US where there are big trunks of things like fiber optic cable coming together to run to other data centers. And so if we came out with, say, a new technology that allows us to transfer data even faster, and we say, well, it'd be great if we could connect up those important data centers that are these hubs of internet traffic to the rest of the country, we should connect all those data centers together with this new technology. Now, that's great, except for one problem. We're saying, hey, we've got a data center here, looks like Chicago, and we'd like to connect it to this other one over here, which it's hard to tell from the graph is probably Pennsylvania or New York. Hard to tell from where it is, probably Pennsylvania. Anyway, how are we going to lay that cable? Is it going to be underground? Wow, that makes it expensive to lay those cables. And so we don't want to lay more of this new cable than we have to. We want to get everyone connected, but we want to spend the least amount of something. Time digging, money are probably proportional to each other. It could be we might want to minimize the number of large highways that we have to go underneath because that's even harder. So we may have some way to estimate the cost of laying a cable between two data centers, and we say, okay, we want to minimize that total cost. Well, minimum spanning tree problem. So this same problem, so the minimum spanning tree and the and the traveling salesperson problem sound like problems that are kind of esoteric. Who does traveling salespeople anymore? Who goes door to door selling stuff? So that's what it's named after, but the problem still appears all the time. So between minimum spanning tree and traveling salesperson, or as we refer to them, MST and TSP, those problems occur in the real world all the time in things like routing cables across the country, routing circuits across a chip, and so these same problems come up over and over again. So for example, we've got a link drawn in there. Once I've got that link drawn in, and then I might say, hey, let's start there. That's a really important one. And then I'll connect it to this other one here, and then I'll connect it to that other one there, and then that one there. Then I might go up to there, would be the next cheapest one, and then erase my markings, and then we might connect it over to there, which doesn't maybe look like the easiest way, but the dollar says that's the best way to connect it. Then we go over to there. Well, those two are really close. We can connect those together, connect them to those nearby, and then another one, connect it down to that one and over to that one, etc. So we can keep building that tree out until everybody's connected, and we've solved the minimum spanning tree problem, and then we can go lay the actual cable. So this is one way to look at solving the problem. It is not the way that the algorithms work, but it is a decent way to solve it visually. If we gave you a problem, we said, here's a graph, here's all the edges in the graph, here's all the edge weights, you could say, well, hey, I see some cycles there. Let's just take out the largest edge weight that's involved in a cycle. So this is sort of solving the problem in reverse. Now, we don't have any of the algorithms that we show that are going to do it this way, but it's a decent way to do it on a problem that's already got the edges shown. You could do it this way on the exam, for instance. If it didn't say use method X and what's chosen next, if it just says what's the minimum spanning tree cost, you could do it like this. Okay, so we've got the graph, and we look at all those edges and the cycles, and we say, hey, there's an edge with weight 120. Let's take that one away. So now our total weight is down to 300, but we still have cycles. So the longest edge involved in a cycle is the edge of weight 100, so let's remove that one. Okay, we're down to weight 200. We still have a cycle. I can't remove 80. 80 has the highest cost, but it's not involved in the cycle. So we got to leave 80 alone. If we took away 80, we wouldn't have spanning anymore. Spanning means to connect everything. So we need it to be spanning in that it connects everything, minimal cost. But we can't say, oh, I've got a minimal cost, but nothing's connected. The cost is 0. No, that doesn't solve the problem. So we can't take away 80, but 60 is involved in a cycle. We can take away 60. So now we're down to a weight of 140. We've got 4 vertices, we've got 3 edges, we've got a connected graph. If we took away any more edges, we wouldn't have a tree anymore. We'd have a disconnected graph. So there's our solution to this problem. Now, what we want to look at is how could we prove that a unique shortest edge must be included. But what we mean by unique shortest edge is like there's an edge of weight 1 and there's no other edges of weight 1. So if there were 2 unique edges, well then certainly one of them would have to be in there. But let's just go with, let's say every edge has a unique weight. Then the shortest edge must be in there. All right. So prove that for the first one. Can you prove it for the second one? Does the second shortest edge, so if the edge weights were 1, 2, 3, 4, 5, etc., can you prove that 2 has to be in there? What about the third shortest edge, 3? Can you prove that it has to be in there? Next for our show a graph, just draw a graph that has more than one MST. And what that means is that they have the same cost, but we pick different edges. So in that one, for number 4, there would have to be some edges that have a duplicate cost, that have the same cost, in order for us to have more than one MST. Same cost, different edges. So think about drawing one of those. Show a graph and its MST which avoids some shortest edge. Hint, there better be duplicate edge lengths there. And then last one is show a graph where every longest edge must be in every MST. All right, what I want you to do, take a few minutes to think about these, and then we'll go through some examples together and some proofs and some examples. Okay, so let's think about how could we prove number one? How could we prove that a unique shortest edge must be in every MST? What are our tools that you learned in 230 for proving things? Well, this one, we could do it via a proof by contradiction. So there's a slide here, so it's got some answers on it. But so the first one says proof by contradiction. So let's assume that we've got a shortest edge and it's not in there. All right, so I've got a graph. All right, so we can see which one is the shortest edge there. And so I say, okay, well, that one's not in the graph. So I'm not going to pick that one, so I'll pick, say, this one, this one, this one, and that one. I'm saying that that shortest edge, not in the MST. Well, now I have a spanning tree. I do have a connected graph. So let's say, I'm going to change colors here. Let's say I were to add that edge. Well, if I were to add this edge in, I would no longer have a minimum spanning tree. It would have a cycle, so it wouldn't be a tree anymore. So if it's not a tree anymore, then I should remove an edge. Well, I choose to remove the edge with the largest weight. Okay, so let's get rid of that one. Well, now I'm back to a spanning tree, and it has a lower cost than the one that used to be in there. It has a lower cost than the one I used to have. So because I've reduced the cost, the original one was not a minimum spanning tree. And so the shortest edge had to be in there to make it minimal. And then we could repeat that proof for the second shortest edge. So we assume the first shortest edge is in there. Let's take the second shortest edge out. Let's say the second shortest edge was that one. So I take that one out, and then I say, okay, well, now I have what I claim is a minimum spanning tree. Well, let's put that edge back in. Well, now I have a cycle, so let's take out the longest edge in the cycle. To me looks like that one. I take that one out, and now I have a slightly lower cost. Second shortest edge has to be in there. Okay, what about the third shortest edge? Can we keep proving this, that every shortest edge must be in the MST? No, number 3 is a problem, because if I had a graph, let's say I just had a graph with 1, 2, 3 vertices. I've got the first shortest edge is in there, second shortest edge is in there. The third shortest edge can't go in if it produces a cycle. So even if I had some more vertices in this graph, like out here, okay, the third shortest edge still can't be in there. I've got to pick some other edge to make the graph connected. So the third shortest edge would be in there if it didn't produce a cycle. But if it produces a cycle with the first and the second shortest edges, then we got to remove it. Okay, so then the questions on the previous slide was, okay, the fourth one is, show a graph with more than one MST. All right, so 4 and 5, and so 4 and 5, 5 said show me a graph and its MST which avoids some shortest edge. Then we could say, okay, well, what about this? Every edge in the original graph is the same length, so I left one of them out. And I could have left any one of them out and still had a different MST. Same total cost, different selection of edges, that produces a new MST. Now we've got a graph in here for number 6, but I think it's slightly wrong, so I'm going to draw it myself. So number 6 said, show a graph where every longest edge must be in every MST. Okay, so let's say I've got a graph that looks like this. Here's vertex, 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 vertex over here, and I say, well, the only edges in this graph are this one, and that one. Those are the only edges in the graph. Well, I have to pick them. I have to pick all of them. All of the longest edges are in the graph, because if I take away any of them, it wouldn't be a tree anymore. So the longest edges have to be in if it's already a tree. There's nothing to take away. It's already a minimum spanning tree if every edge is needed just to keep it spanning, just to keep everything connected. Okay, so that's the end of our definitions. Now, what we're going to do is we're going to look at 2 different algorithms for producing an MST, and they're both named after the people who created the algorithms. The first one is named Prim's algorithm, and Prim's algorithm says what it does is it finds an MST on an edge-weighted connected undirected graphs. Now, it also says it greedily selects edges one by one and adds them to a growing subgraph. Now, greedily, we've got another chicken and egg problem here. So we're going to be doing a lecture in, I guess, tomorrow. So tomorrow is going to be our lecture on algorithm families. And when we do algorithm families, we're going to do definitions of each of these different types of families. But we need to get this lecture done so we can have you ready for Project 4. And also, it's hard to talk about algorithm families when you don't have any example of an algorithm from that family. So what greedily means? So what does a greedy algorithm do? A greedy algorithm says, I'm going to pick whatever looks best right now. I'm going to make a very limited choice on the data I have right now. I'm going to pick the best possible thing I can do that doesn't violate any constraints. So we would pick the smallest edge that doesn't produce a cycle. And the other thing about a greedy algorithm is it never goes back and changes its mind. Once it's made that best decision right now, it never says later on, oh, that was a bad choice, let's go undo that old choice, which would then affect a whole bunch of other choices made after it. So greedy algorithms never redo previous choices. Now, the goal here is there are ways to be greedy. There's different ways to be greedy. In fact, we're going to show you 2 different greedy algorithms. The other thing is that for this algorithm to provide a minimum spanning tree, it must be the case that all of those greedy decisions were the best long-term decisions. Not only did I make it based on just the data I had right now, it was the perfect choice to make. There was no better choice to be made. There might have been an equivalent choice, like, hey, I've got a graph where my edges are all the same weight, 1, 1, 1, and 1. Well, I can pick any one of those. At least one of them is going to have to be in the minimum spanning tree. So that's what a greedy algorithm does. It makes the best choice it can make right now, and it never changes its mind. And then if it does solve the problem, it has to be the case that all of those locally optimal choices added up to a globally optimal solution. Now, the way prims is going to work is it's going to start with a single vertex. It's going to pick a vertex, and then it's going to start picking edges and adding to them to the existing subgraph. So what we're going to do is we're going to initialize a tree. We're going to say, hey, here's a tree. I'm going to arbitrarily pick a vertex. Arbitrarily means it doesn't matter how we pick it. We could make, if we're going to have to write code, we could write a deterministic choice, like the first one alphabetically is the one I pick, is a simple way to do it. Or I've got some sort of list of vertices. I always pick the first one in the list. I don't care what its name is, just the first vertex you list, that's the one I pick. Because I don't know how many there will be when I write the code, I can't say, ooh, pick the 18th one. Well, maybe there's only 12. So let's just pick the first one. So we pick one arbitrarily, and then it says we grow the tree by one edge. We say of all the edges that connect the tree to vertices not yet in the tree, find the minimum weight edge and add that vertex to the tree. So we say I've got this vertex and I've got all these other vertices that aren't connected to my growing tree yet. I want to say of all the edges that would connect the tree that I have to the vertices that are not in the tree, find the smallest one. That one's got to be in there. We pick that one, we add that vertex to the tree, and that edge becomes part of our minimum spanning tree. And then we just keep doing this over and over until all the vertices are in the tree. So we've got to do this v times. If there's v vertices, we got to do this process v times. We've got to pick the initial one, and then we've got to pick v minus one others. All right, so it says we're given a graph g of v comma e, and it says this is the original description of the algorithm. This is not necessarily how you have to write it. It can be written much simpler than this, and our timing is based on a simple approach. If you use this approach of innies and outies, if you're not really careful about it, you could make it slower. So we're going to start with two sets, and they could just be logical sets. They don't have to be actual sets in our code. So we have two logical sets, the innies and the outies. The innies are the ones that are in our minimum spanning tree. That set is initially empty. The outies are the ones that are not in our tree. That's initially all the vertices. So we select one vertex to be an innie. We select one, and that becomes the root of our tree. Then we keep doing this process until there's no one else in the outset. We pick the outie with the smallest distance from any innie. We move that v prime over from the outies to the innies, and we keep doing this. And there's an implementation issue. When we do this, how do we pick that smallest distance? We could do a linear search, we could do a priority queue, etc. So we're going to look at different ways to implement it. Now, there's three pieces of data needed to run prim's algorithm. We have to record for every vertex, we have to record, has this vertex been visited? Really what this means, this KV, is true or false. It's saying if it's false, you're an outie. If it's true, you're an innie. So we're going to record for every vertex. We're going to record, is it in the tree yet? It's initially false for everybody. The distance, the minimum distance from this vertex to anyone in the tree. And initially, that's going to be infinity for everyone except the root. The root's going to have a distance of 0. That's how we pick the root, is we say, hey, the root is a distance of 0 from the tree because it's the root. It's the start of the tree. And we also have to record the predecessor or the parent. Which vertex is this one connected to? And initially, that's unknown for everybody. Now, really, we don't want to do 3 vectors. 3 vectors is parallel vectors is always a recipe for future growth issues. Now, granted, here we told you there's 3. But my favorite example is if we're creating a student project, a student tracking project, I wouldn't say, oh man, I need a vector of names and I need a vector of majors. That's what I need. I need 2 vectors, done. And then later on I discover, oh wow, I need a vector of phone numbers for them, and a vector of addresses, and a vector of cities and states and zip codes and countries, and then I need a vector of GPAs, and I need a vector of minors, and I need a vector of that. And now I've got like 7 vectors to represent a student. Well, instead, let's just make a student object, either a class or a structure, and then let's make 1 vector of that class or structure. And if I decide I have to add something to it, I still only have 1 vector. So we don't want to have 3 vectors here. We want to have 1 vector with k, d, and p in it. And you can call them k, d, and p. You can give them slightly more readable names without going too long, like known, weight, and parent or predecessor, or previous, or PRED for predecessor. So you can name them K, D, and P, and people that know Prim's algorithm will be able to read your code, or you can give them slightly longer names. Not a big deal. So Prim's algorithm says before the loop starts, so outside of the loop, it says pick a starting point and set its distance to 0. So remember, initially everybody has a distance of infinity, everybody is false, they are in the outset, we don't know who anybody's predecessor is. Then outside the loop we say let's set the starting point's distance to 0. Then you say loop v times. Now it says in parentheses we're doing this until every kv is true, but really if I was writing the code I would write it as a for loop. One thing to watch out for in the for loop here. This for loop is not an index. It is a count. So I would write this as like for count is equal to 0, count is less than some size. And I'm not going to use count as an index. I see people every semester who want to use like I here, and then they go, oh, I've got I must be an index. Got to use it as an index. It's not. It's just counting. Okay, so we loop v times. Step 1 says, of the set of all vertices for which kv is false, select the one with the smallest distance. So of everybody who's false, of everybody who's out, pick the one with the smallest distance to someone who's in. So that's going to have to be like a loop or something there. Then step 2 says mark it as true. Then step 3 says for every vertex w adjacent to the one we just picked, if that adjacent one is false, test whether we've got a better way to reach that vertex. So test whether dw, that's what's in the tree, or sorry, that's what's in the table. Check if dw in the table is greater than the distance from v to w. So basically we're saying, did v find us a shorter way to connect w to the set of innies? If it is, we change dw to be that distance that we calculated, and we set the previous of w to v. Now, the variable names here, you can use different variable names, obviously, but it's going to become a lot more clear when we run through an example. And the first example we're going to do is, what if we just did this with loops, without a priority queue? What if we just did this with nested loops? Step 1 is a loop, step 3 is a loop. So we've got this outer loop that's going to run v times, or count is going to run less than the size. Size would be the same as the number of vertices. So we're going to run this outer loop, for loop. We're going to have step 1 is a loop, step 2 marked as true, step 3 is a loop of update the false neighbors. Now, when you implement this, you're going to look at it and you're going to say, ooh, I can reorder this. I'm going to, outside the loop, I'm going to say the first one is true. Why should I go through step 1 and go find the smallest? I know the smallest false one is 0. I know which one it is. I'm going to mark it as true outside the loop. And then I'll skip straight to step 3. And then I'll do step 1, and then I'll do step 2. Don't do it. Don't do it, don't do it, don't do it. We end up with students every semester who cannot get it working because they decided to reorder it. They decided to mark something true outside the loop, and then they want to reorder these simple steps, and they do a simple reordering that ends up wrong. They run the loop too many times. They reorder it wrong. They keep track of the wrong thing. It's really, really, really easy to implement this, and it's so much easier to get it right if you implement it in the order that we list. So there's nowhere that says set something to true outside the loop. It says set somebody's distance to 0 outside the loop. So make sure that you follow what we said here. Because if you implement it in the different order, I might just say, no, you decide you know better than us, you're on your own. Go figure out your bug. Or do what we said in the first place and implement it in this order. Okay, what we're going to do is run through an example. It's going to make this a lot clearer if we do an example. So I've started out, I started out with everybody's false, everybody's infinity, and everybody I don't know your predecessor. And then, just to save one slide, I started out with everybody in the table was infinity. This one used to be infinity, and I crossed it out and put a 0 there. All right, so we've done the initial outside of the loop work. We've got our table, our prims table. It didn't say that V had to be a part of the table. We need some way to identify the vertices. It's going to turn out in project 4, we're going to tell you the vertex names are their indices. So really this would be, in our project, this would really be like, hey, this is 0, 1, 2, 3, 4, 5. It doesn't need to be inside of the vector. It's the index to the vector. It's outside the vector. So in our example here, we list V because it was easier to use letters than numbers, because we got numbers for distances, numbers for vertexes. It would make the graph a little bit harder to read. But when you implement it, V is not going to be inside of the table. It's going to be the index into the table. All right, so step 1 says find the smallest one that's false. So to do that, what I need to do is I need a current distance. And because I've got a limited amount of room here, I'm going to say my current D, my current distance is infinity. Why infinity? I haven't looked at anything yet. I don't know what's better or worse than anything else, but I know nobody's worse than infinity. So I initialize my current distance to infinity. This is before the step 1 loop. So we've got an outer loop that says, hey, we got to loop V times. Step 1, to get ready for step 1, I'm going to set up my current distance is infinity, and my current vertex, or I'm just going to say current, my current is, I don't know. The compiler might force you to initialize it, so I could put something in there like -1 or whatever. We might have to initialize it, but I don't know anything. So now it's time to run the loop. This is the step 1 loop. Find the smallest false one. Okay, so I go through the table. A is false. It has a distance of 0. 0 is better than infinity. So A is my best one so far. But I've got to loop through everybody. B is false. Infinity is not better than 0. C, D, E, F, all the same. They're all false, but they're not better than 0, so we don't pick them. Okay, we're done with step 1. Step 2 says, mark that current vertex. That was what was in the slides called V. Lowercase v was what I'm calling current. So take V and mark it as true. Aha, okay, A, you're true. And in the graph, if we're not redrawing it, I could just say, hey, let's circle that to mark it as true, just so I remember it's been picked. And then step 3 says, go and update the false neighbors. All right, so I say, all right, well, let's just loop through everybody. I don't know who's a neighbor. I've got to loop through everybody. And I say, okay, well, A is true. It's not false, so I can't look at it. B is false. What's the distance from A to B? Looks like 13. Is that better than the infinity in the table? Yeah, it is. Hey, I found a better way to get to B. I can get to B at a distance of 13 if I get there from A. And that's what step 3 says. Let's go back for a second. Step 3 says, for every vertex that's false, if it's adjacent to V, test whether the distance in the table is greater than the distance from V to W. If it is, change the distance and set the predecessor to V. So that's what we did here. We changed the distance and we changed the predecessor. So now, what about C? Okay, A to C is 8. 8's better than the infinity in the table. And I have to get there from A. Right, what about D? A to D is 1. That's better than the infinity in the table, so let's put a 1 there, and we get there from A. Now E. Now in this graph, looking at it, you can see it's not connected. But in your project, I'm going to give you another tip for the project for part A. When you code part A, you're going to have these things, locations in the spaceship. We're doing Among Us. So if you like the game Among Us, you'll like the project. If you don't know Among Us, that's okay. You can still understand everything in the project without knowing the game. Just understand it's a graph. There's locations. But one of the restrictions in our project 4, part A, is you cannot connect someone in the lab to someone not in the lab without going through a quarantine zone. Now, that'll make more sense later. But the point is, Prim does not know anything about labs and the rest of the spaceship and quarantine zones or anything like that. Prim has a helper, though. Prim says, hey, helper, what's the distance from A to E? The helper looks and says, well, A's in the lab and E is outside of the lab. You're not allowed to connect those. But I'm the helper. All I'm allowed to do is tell Prim a distance. So A is inside the lab, E is outside the lab, and it's not in the quarantine zone. I know Prim's not allowed to connect those, but I've got to give Prim a distance. What distance do I give it? I tell Prim infinity. The distance from A to E is infinity. And Prim says infinity, well, that's not better. I ignore it. I don't connect A and E. So that's the way to make this project simpler, part A simpler. Write Prim very straightforward, but have a helper function or functor that Prim calls to say, hey, helper, what's the distance from A to E? If the helper says, hey, those can't be connected, the helper says infinity, otherwise it does a calculation and returns a number. So here the helper would say infinity, and Prim would say, wait, infinity is not better than what's in the table. I don't update the table. Okay, helper, what about A to F? Infinity, that's not better than what's in the table. I don't pick that. All right, we're done with step 3. We've updated all the false neighbors. So now we're going to update the slide. There's the update. And now we say, hey, we got to go back to step 1. We've still got the outer loop. We got to do this until everybody's true. Go back to step 1. Step 1, find the current distance to the current vertex V. Current distance is infinity. Current vertex is -1. Now, find the smallest false one. A is true. We can't even look at it. B is false. 13 is better than infinity. So it looks like, hey, B is our potential best false one. Okay, let's move on to C. C is false. 8's better than 13. Hey, maybe C is the one. Let's move on to D. D is false. 1 is better than 8. Maybe D is the one. E is false, but infinity is not better than 1. F is false. Infinity is not better than 1. There we go. We found our current vertex, or V. So we've picked D. We mark D as true. That was step 2. We mark D as true. Then we've got to go to step 3, update the false neighbors. Really, we update anyone who's false that has a better distance. So I go, A is true, can't change it. Once someone's set to true, they never get looked at, they never get changed, and they never ever get changed, and they never get looked at again until we're done. So I say A is true, can't look at it. B is false. Okay, what about the distance from D to B? Helper. Helper says infinity. I say, that's not better than 13. Don't update that. All right, C. Helper, what's the distance from D to C? Helper says 5. I say 5. Hey, that's better than the 8 in the table. Let's update that 8 to be 5. If I change the predecessor to what? D. So I've found a better way to get to C. What about D? It's true, can't touch it. E is false. Hey, helper, what's the distance from D to E? Helper says 4. I say, hey, 4, that's way better than infinity. 4 if I get there from D. What about F. F is false. Helper. Helper says 5. All right, helper. 5 is better than infinity, so I put a 5 in there and I mark its predecessor as D. Notice I didn't call the helper twice. I called the helper, I remembered what it said in a variable, and I used it twice. Don't compute things twice. Compute them once, remember them, use them twice. Okay, so we're done with step 3. We've updated all the false neighbors. Okay, update the table. So there's, I think Professor Darden got a little bit off on his line there. Okay, so we're showing basically D is true and that edge of weight 1 is in the MST. All right, so we got to go back to, we're still in the outer loop until everybody's true. Current distance is infinity. Current vertex is -1. Find the smallest false one. 13 if I choose B. 5 if I choose C. Now, what if, I'm just going to do a what if here for a moment. What if this one was also 5? And I've got 3 5s that are false. Which one do I pick? Well, I pick 5, C, and then I get to D is true, can't pick D, and I get to E, and I say, hey, E is 5. Is 5 better than 5? No. Okay, then I don't pick E. Is F better than 5? No. Okay, I don't pick F. It doesn't matter, but I would tend to stay with the best. If you don't improve it, you don't get picked. Does it make a difference? No. We would just end up picking them in a different order. But I just found it easier to write the code to say, hey, the new edge weight's got to be better than my current best. It can't be the same. But that's not the case. When we get to E, E is 4. 4 is better than 5. F, F is false. 5 is not better than 4, so we're done with step 1. Step 2, mark E as true. And then step 3 is update the false neighbors. A is true, can't touch it. B is false, but E to B is infinity. C is false. Ooh, but E to C, the helper says 3. 3 is better than 5 if we get there from E. D is true, can't touch it. E is true, can't touch it. F is false. The distance from E to F, we call the helper. E to F, distance is 2. 2 is better than 5 in the table. So we change it to 2, and we would say we get there via E. All right, we're done with step 3. Update the slide. All right, so we got to go through current distance, current vertex, or current distance, current vertex. All right, go through and find the smallest false one. True, not it. B is false at 13. C is false at 3. D is true, E is true, F is false at 2. F is the one. Step 2, mark F as true. Step 3, update the false neighbor. So A is true, can't touch it. B, well, distance from F to B, helper says infinity. That's not better than what's in the table. C is false. F to C is infinity. Don't do that. D is true, E is true, F is true. Done updating the neighbors. All right, so we've updated the slide now. So we got to go back through. Current distance is infinity. We're back to step 1. Current vertex is -1. All right, who's the smallest false one? Not A. A is true. B is false at 13. C is false at 3, and that's better than 13. D, E, and F are all true. They're not candidates. It's C. Mark C as true. That's step 2. Step 3, update the neighbors. Well, A is true. We can't update that. B is false. C to B, helper, what's the distance from C to B? 15. 15, that's a real number, but it's not better than what's in the table. Don't update it. C is true, D is true, E is true, F is true. Notice, this is another thing that students do. They say, ooh, I've got to make sure that I don't pick C because C is the one that I'm working on right now. No. All I do is look at it and I say, hey, if C is true, I don't consider it. So you don't need to say, If it's not the current vertex and it's false, just say, if what's in the table is false, I can consider it. You don't have to check if it's the current vertex, because if you do things in the right order, hey, I did step 2, I marked it as true, then step 3 will never consider it because step 3 only considers false ones. Okay, so C is true, D, E, and F are true. We're done updating the neighbors. We're done with step 3. So loop, outer loop has one more time to go in that count. So we go back through step 1. Current distance is infinity. Current vertex is -1. Find the smallest false one. A is true. B is a distance of 13. True, 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 true. They can't use them. All right, done with step 1. Step 2, mark B as true. Step 3, update the false neighbors. Okay, we go through the table. Everybody's true. There's no one to update. We are done. And now, we don't actually, in our code, we don't actually have the graph on the right. But what we do have is we've got our trims table. How do I know what's in the graph? Well, I just go through the trims table. I know up front, I remember, hey, I said the first vertex, I'm going to mark that one as a distance of 0. So that one doesn't have a predecessor. So let's just loop from vertex 1 to the end. And what I'm going to say is, hey, I want to list the, in the project we have to list the weight. So the weight is going to be the sum of the D column, looks like 16, 17, 21, 23. So we'd say like 23.00, we'd say that's our total distance, and then we have to list the edges. So the edges would basically be BA. In the project, there's a caveat. When you list an edge, you must list the smallest vertex first. So instead of listing BA, I would list AB, A space B. Really, in the project, it wouldn't be A and B. It would be basically 0 space 1, because that's their indices. So we'd go 23.001. The next one says, so it'd be 0, 1, 2, 4. DA would be 0, 3, because I list the smallest one first. DE would be 3, 4. And EF would be 4, 5. So that's what your program would produce. It'd say, this is the total cost, and here's my list of the edges that I have picked. I've picked the edge from 0 to 1, 2 to 4, 0 to 3, 3 to 4, 4 to 5. Now, one thing about project 4. Part A of project 4. All the parts of project 4. You do not have to have exactly the same output as us. You have to have a valid spanning tree. It must be minimal. And the autograder is going to grade each part with a different judge. So in the past, the judge is a part of every project and every lab on the autograder, and it says basically, if your output is the same as ours, I judge you to be correct. Well, project 4 has a different judge for every part that says, hey, does your total make sense? Like, does your total add up with all the edges you listed? If I add up all those edges, do they add up to your total? Does your list of edges produce any cycles? Is every vertex connected by the edges you listed? If all those things are true, then must be a valid MST. And part B and C are judged in a similar way. Does your output match the input, and is it a valid solution to the problem? Then we judge it to be correct. So you could list these in any order. Now, in our sample output for project 4 part A, we actually list the edges in the order they got selected. Kind of tricky that, seeing as how we had to output the distance first. But we did it for you. So our output could be different than yours. It could still be right, though. But the important thing is it an MST? Does it have, if it has the same cost as ours, that's a good first step. If it has edges that produce a tree with no cycles, and the cost of those edges adds up to the number, it's a valid MST. Also, Project 4 spec, when it comes out, which don't ask on Piazza, it's all set. 12:01 a.m., it'll be visible on Canvas. So we've got like 12 hours and 42 minutes. So when it's visible, you'll be able to look at it. There's video, there's another video. there's a link to a specific page on the autograder that there isn't a link anywhere else other than the Project 4 spec. There's a visualization tool that you can load up an input file and an output file and say, hey, you tell the autograder web page this represents an MST, and it'll graph it for you. Okay, so what I want you to do is take a few minutes and MST this using prims. So if it says start at node A, so what that means is that everybody starts out as false. I'm going to leave the falses out of the table because if there's nothing there, it must be false. If there's no T there for true, it must be false. Everybody has a distance of infinity except for A. That's what it means by start at A. So A has a distance of 0. Everybody else has a distance of infinity. And nobody knows who their predecessor is. I'm just going to leave those blank. So run through this. Take 2 minutes to do it. I'm going to get a drink of water and I'll be back. Okay, so let's run through this really fast together. Okay, so I'm not going to list everything out. So we find the smallest false one, that's A. Mark it as true. Okay, then we've got to update the neighbors of A that are false. Okay, B is a distance of 1. That's better than infinity if I get there from A. C is a distance of 3. That's better than infinity if I get there from A. D is not adjacent, it's a distance of infinity. E is a distance of infinity from A. Okay, so that's done. We've updated neighbors. All right, smallest false one looks like B. B gets marked as true. Then let's update B's neighbors. We can get from B to C at a distance of 4. That's not better than 3. We can get from B to D at a distance of 6. That's better than infinity. And we can get to E at a distance of 7. That's better than infinity. And we update the predecessor also, would be B. Okay, go through the table. Step 1, find the smallest false one. Looks like C. C gets marked as true. Then we update the neighbors, the false neighbors. So D, C to D is a distance of 5. 5's better than the 6 in the table, so we get there from C. C to E is infinity, so that's not better than 7. Done there. Okay, step 1, smallest false one, D. D gets marked as true. Update the neighbors. Well, the only neighbor to update is E. D to E is 2. 2's better than the 7 in the table, and its predecessor would be D. Okay, back through the outer loop. Step 1, smallest false one is E. Step 2, mark it as true. Step 3, update the neighbors. There are no false neighbors to update. We're done. So there's our minimum spanning tree. We've got a total cost of 0 plus 1, 3 is 4, 5 is 9, 2 is 11. So we got a cost of 11, and our edges, so it'd be like 11.00. Actually, let me write it up here. So it'd be like 11.00. Our output would be, first row is not part of the output because it doesn't have a predecessor. Next row would be BA would be 0, 1. CA would be 0, 2. DC would be 2, 3. and ED would be 3, 4. So that's what our output would look like if we gave this to the project 1, part A. And then basically everything we need to know is in the table. And there we've got the whole table filled out with the crossouts and everything. Okay, so what if, so this is the what if we did linear searches? What if step 1 was a for loop and step 3 was a for loop? So then we've got this outer loop that's going to run v times. We've got step 1 has a cost of O of v. I loop through the table, checking false ones, finding a better one. Step 2 is O of 1. Step 3 is at most O of v, because I've got to look at them. If they're false, I got to check the weight. That calculation is O of 1. So I say, is it false? That's O of 1. Calculate the distance. That's O of 1. If it's better, update the table, update the predecessor. Those are all O of 1. And there will be at most v of these that we have to check. Well, we got to check all v of them. And then at most there will be v of them, v minus 1, that have to change. So step 3 is O of v. Whoops, sorry. So step 3 is O of v. So we've got an outer loop. So we've got basically v times our outer loop of v plus 1 plus v is O of v squared. So we've got the outer loop runs v times. Step 1 cost is v, step 2 cost is 1, step 3 cost is v. So it's v times v plus 1 plus v gives us O of v squared. So not too bad. It finds a minimum spanning tree in quadratic time. All right, what if instead of linear searches, what if we did priority queues? So what if we said, hey, let's use a priority queue to solve this? So this first part is all the setup. I say, okay, I figure out what n is, that's easy. Then I say create the table. It says the create the table takes O of v time, because however I do it, I've got to put the falses and infinities and stuff in that table. So that takes O of v time to make that table size v with false infinities in it. Okay, create an empty priority queue, that's O of 1. Set table S0 to a distance of 0, so that's O of 1, change somebody's distance to 0. And then I've got to insert into the priority queue S0 at a distance of 0. So I add that to the priority queue. It's a cost of 1 because I know right now it's empty. Later on it won't be a cost of 1, but now it is because we know right now it's empty. So this is all initialization. Now we got to loop while the PQ is not empty. And the PQ is not empty is going to run E times. So E, we can think of this O of E up here should really be like over to the left just a little bit. It's like the outer loop. So we're going to do this stuff E times. E times we're going to have to do stuff. So the amount of work that we have to do in that loop, at first it says, get the minimum. Do a top and a pop from my priority queue. Well, the things get inserted into the priority queue, right? But we're never going to use an edge twice. So since we're never going to use an edge twice, that's why the outer loop is O of E. We're never going to use an edge twice. So it's going to be O of E, is how many edges we're going to have to add to the PQ, how many we're going to have to take out, etc. So we're going to have to do this with E edges. We're never going to repeat an edge. And so if we do this E times, then the maximum complexity of top and pop from a binary PQ would be log of E. So that's where the E and log E come from. So we get the top and we pop it out, and then we have to check, is it not known? And this is important because we could have put something in. For example, I might have said, hey, I know how to get somewhere at a distance of 5, and I put it in there, but what comes out is a distance of 2. And so I say like, hey, I can get to D at a distance of 5. So I put D5 in there. Then I take out someone else, like B, and B says, hey, I know how to get to D at a distance of 3. So now D5 and D3 are both in the PQ. D3 comes out first, and it says, if it's not known, mark it as true. So D gets marked as true. At some point later, though, D5 comes out of the PQ and we say, oh, whoops, D's already true. This is outdated information. We found a better way to get to D at a cost of less than 5, so we don't need this one. And there's no else clause. This is the whole if, that's the whole of the if, and there's no else. So that's why we need the if, though, because we could have D5, D3 both in the PQ. D3 comes out first. D5, when it comes out, is no longer needed. It's outdated info. So we say if it's not known, so if we haven't already found a way to get to this vertex, mark it as true, and then for everybody, it says for every vertex I that's adjacent to vertex 0. So this is basically saying let's run through the adjacency list. Let's run through the adjacency list. How many things are in the adjacency list? O of 1 plus E over V. That's the cost. O of 1 is to get to the head of the linked list. E over V is the length of the average list. So we say for everybody in the adjacency list, calculate the distance. If it's less than what's in the table, then we update what's in the table. So these are the same as the other one. Mark the new distance, mark the new predecessor. And also, if we've found a better way to get to someone, we got to add them to the PQ. Adding them to the PQ takes log of E time. So the complexity of this whole thing is basically E times log E plus a bunch of constants, E over V, plus some constants, log E. So we've got I'm going to go up to the top here, so we've got E times E over V plus a bunch of constants plus 2 log E. Now wait a minute, we said adjacency list here, right? If this is an adjacency list, it better have been a sparse graph, right? We said that yesterday. So if it's a sparse graph, what is E divided by V? E is proportional to V. E divided by V should be a constant. So this is equal to E with a bunch of constants plus 2 log E gives me O of E log E. So that's our complexity with a priority queue, assuming it really is a sparse graph. What if it's not a sparse graph? Well, then E is V squared, right? E is proportional to V squared, and I've got V squared log V squared, which is worse than the nested loop version. Okay, so the complexity here is basically, we already went through all of that. We've got E, etc. Yeah, we already did all that. Okay, so the complexity summary is, if we have the simple nested loop implementation, we get O of V squared. If we do heaps, it depends. It has to be a sparse graph. If we're going to use the priority queue version, it's got to be a sparse graph and adjacency list. And if it's not, if it is really a dense graph and E is proportional to V squared, then we get O of V squared log V squared. And that's slower than we've just gone with the nested loops. So the takeaway from this is, if it's a dense graph, use the simple nested loop implementation. If it's a sparse graph, you could use priority queues, or better yet, move on to a different algorithm. Turns out Kruskal's algorithm is better with sparse graphs. Okay, so let's move on to Kruskal. So Kruskal's algorithm, same exact problem. What we're going to find, how it does it and how it grows it is different. So this part is the same. It is also a greedy algorithm. It says it's greedily going to select edges one by one and add to a growing subgraph, and it's going to grow a forest of trees. So it's going to pick edges. It doesn't care if it's connected to the current innies or outies or not. There's no idea of innies and outies here. Kruskal basically says, pick me the smallest edge that doesn't produce a cycle. Connected, disconnected, I don't care. Just pick the smallest edge that doesn't make it illegal. And eventually, so if it says, hey, I pick this edge and then I pick that edge, well, they're not connected. Eventually, I'm going to have to pick an edge that'll connect those together, and my forest of trees becomes one big tree. All right, so Kruskal's algorithm says first thing we've got to do is pre-sort the edges. We got to take the list of edges and sort them by their edge weight. So pre-sorting all the edges, it says, takes O of E log E, which is, remember, this is only going to work if it's a sparse graph. Because if it's a dense graph, this would be V squared log V squared. Well, that's going to be slower than Prim's nested loop. If it's a dense graph, we use Prim's nested loop. So Kruskal's really is for a sparse graph. So it's E log E, which is the same as E log V, which is the same as V log V when E and V are proportional to each other. Okay, so it says we're going to try to insert in order of increasing weight. Some edges we will not use them because they would create a cycle. And so the initial edges, the first 2, 3, 4, if there's like 40, 50,000 vertices, maybe the first 1,000 are all disjoint. Maybe we've got 1,000 little tiny trees which are all going to grow together into one big forest and one big tree in the end. So it could be disjoint. So Kruskal's algorithm says, let's pre-sort the edges. Now, we could take the time to say, okay, let's write down all the edges and let's go through a quick sort and blah. If we're going to do it visually, we can do it without even doing the sorting. We just have to be super careful. But we could. So, whoops, sorry. I was thinking we had the edges pre-sorted. We don't. So we could go through and pre-sort all the edges and go through everything. But we can do it by hand if we're careful. So I look through and I say, well, I know there's no edges of 0 or negative. Let's find, is there any edge of length 1? Oh, there is. Okay, edge of length 1, you're in. More than one edge of length 1? I don't care. One of them is in. So, edge of length 1, you're in. Is there any edges of length 2? Yes. Does it produce a cycle? Well, no. Remember we said the first 2 edges can't produce a cycle. But really, our code is going to pick, is going to do the whole algorithm of, hey, I pick AD. Does AD produce a cycle? No. Okay, AD is in. Then I choose EF. Does EF produce a cycle? No, EF is in. And it's disconnected. It's part of a different subgraph. Okay, next one, edge weight of 3. Does DC produce a cycle? No. Okay, CD is in. All right, next lowest edge weight is 4. Does edge 4, D to E, sorry, I think I misstated that one. It's not C to D, it's C to E. It's really hard for me to see black on dark purple or blue, whatever that is. Anyway, so CE didn't produce cycle, so we picked CE. Now we've got DE. Does edge of length 4 produce a cycle? No. So let's choose the edge of length 4, and hey, they're all part of the same bigger subgraph now. Okay, how about an edge of weight 5? There's 2 of them. Which one do I pick first? Who cares? I got to pick one of them. Let's go alphabetically. So CD comes before DF. So CD, edge of length 5. Does it produce a cycle? Yes. Okay, can't pick it. Other edge of length 5, DF. Does it produce a cycle? Yes. Can't pick it. Edge of length 6. There are none. 7. There are none. 8. Okay, edge of length 8. Do you produce a cycle? Yes. Can't pick you. Okay, 9, 10, 11, 12, 13. Edge of length 13. Does it produce a cycle? No. Okay, so we can pick the edge of length 13. Edge of length 15. Does it produce a cycle? Yes. Can't use you. Okay, I've considered every edge. I've got a minimum spanning tree. So that's how Kruskals work. Sort the edges, pick them as long as they don't produce a cycle. Now, the sorting, like we said, takes E log E or E log V time. That happens to be the bottleneck of the algorithm. That is where the bulk of the time is spent, is in the sorting. So we want to make sure we've got a log, an n log n or an e log e sort. Okay, so that's the bulk of the work is that. So then we've got to loop over the E edges. So we've got to loop E times. It says discarding an edge is trivial, adding an edge is easy. Think of it, we could keep like a vector of edges we picked, or we could just output it. Whatever we do, it's O of 1 to add it. And when we say discarding, we're not actually taking it out of the data structure. I'm just looping through the sorted edges. I'm saying you're in, you're out, you're in, and I either add them to a vector, which is which edges I've picked, or I don't add them to a vector of which edges I've picked. Either way, it's O of 1. It's not even amortized O of 1 because I know up front how many edges am I going to pick? V minus 1. If there's V vertices, I've got to have V minus 1 edges in the minimum spanning tree, so I could reserve the size of my vector. So it really is O of 1 even if we add them to a vector of which edges we're keeping. So discarding or keeping is easy. The hard part is deciding, should this one be kept or should it be discarded? That's the hard part. And we have to say, if it produces a cycle, we don't keep it. If it doesn't produce a cycle, we do keep it. And the idea here is that as long as that takes less than log E time, then it'll be less than the sorting. Because remember, we got to run this loop E times. As long as the total work in here is less than log E, then that still is the bulk of the work, and we are not slowing it down. So the key idea here is if I want to, so I'm looking through my list of sorted edges, and I see the edge VI, VJ. Well, if VI and VJ are already connected, then the new edge would produce a cycle, so I don't take it. So I need to maintain a disjoint sets. I need union find. So this is where the union find data structure that we did a while ago, like back before the midterm, is important. If we're going to implement Kruskal, we need union find. So what we've got here is we've got a slide that has everything in it, including all of the representatives and everything. Now, you don't have to do all of that, but it would help you understand it better. So initially, everybody is their own representative. All right, so what I want you to do is take 2 minutes, run through Kruskals, and then we've got animated slides that are going to show you the whole thing, including the representatives. Now, one thing I'll show you, I'm just going to move forward by one slide here, is that we've got the representatives. Hey, everybody's their own representative. I already did that. And we've got the edge weights sorted for you. So there's the edges in sorted order. And then so we're going to say, hey, AB. We pick AB. Does AB produce a cycle? No, so we pick it. And so run through Kruskal's algorithm with this, and we'll come back in 2 minutes and step through it. Okay, so Kruskal's algorithm is really easy if you don't bother with the representatives, but we've got the animated slide that does the whole thing. So let's go through it together and we'll understand union find a little bit better. Okay, so we say What about AB? We ask A, who's your representative? A says A, B says B. Because they have different representatives, then a union would be safe. So we choose that edge, and we have to update to say, whoops, I went forward a little too early. We have to say, hey, somebody changes their representative to be the same as the others. I always pick the second one. So when it's AB, B is the second one is the one that changes. So with AB, B changes its representative to be A, and then we start considering the next edge, DE. We do a find on D, a find on E. They say we have different representatives. We say, okay, that would be safe to keep. And one of you has to change. E, your representative is now D. Then we consider the edge AC. All right, we do a find on A and a find on C. A says A, C says C. They have different representatives and they can be unioned. And so we have to change someone, C. C changes its representative to A, and we keep that edge. All right, what about the edge BC? We do a find on B. B says A, and we don't stop there. B says A, and A says A, so therefore we know we've found the ultimate representative of that group. So B's ultimate representative is A. We ask C, who's your representative? C says A says A. A is the ultimate representative of C's group. They both have the same representative. They are already together, so we cannot pick the edge BC because it would have produced a cycle. Okay, moving on. CD. All right, we ask, who's your representative? C says A says A is the ultimate representative of that group. D says D, that's the ultimate representative. They have different representatives. A union can occur. So we would change D's representative to be A, the same as C's representative. Move on to the next edge, BD. All right, BD, we ask B. B says A says A, that is the ultimate representative. We ask D. D says A says A, that's the ultimate representative. B and D have the same representative, therefore they cannot be unioned. Now you might say, hey, Dr. P, haven't you already picked 4 edges? Couldn't we stop? Yes, but it wouldn't make as good an example because we want to go through what happens with the union find data structure. So then we ask about BE. We do a find on B. B says A says A is the ultimate representative. We also ask E. We ask E, who's your representative? E says D says A. We have to keep going until someone says, I am my own representative. We got to keep going. So E says D says A says A, that is the ultimate representative. But path compression occurs. As the recursion unrolls, we change everybody's representative to whatever find recursive call said, so E changes its representative to A. Now the find is actually done. B said A, E said A, path compression has happened because B and E have the same ultimate representative. They're already part of the same group and a union cannot be done. We can't pick that edge, and we're done. Okay, so summary here. So the MST is the lowest cost subgraph that includes all the nodes in the graph. It has to keep them connected, and it's got to be a minimum cost. But if we start with a connected graph, we got to keep it connected. We've got 2 algorithms, prims and Kruskal's. So for prims, we are going to iteratively add the closest node to the current tree. We add an outie to the list of innies, and it's going to be similar to Dijkstra's algorithm, which we haven't looked at yet. But when we look at Dijkstra's algorithm for shortest paths, we'll find that it really reminds us a lot of prim, and there's only one minor difference. But when we get there, we'll see that. And so prim is O of V squared or O of E log V. Kruskal iteratively builds a forest by adding minimum edges that don't produce cycles. Both of them don't produce cycles. That wouldn't be a spanning tree. So it builds a forest by adding a minimum edge that wouldn't produce a cycle, and we get E log V. Now, If we've got a dense graph, we must use the nested loop prims version. If we've got a sparse graph, they both have the same theoretical complexity, E log V, but it turns out in implementation, Kruskal is faster. So we've had multiple people on 281, both faculty and staff, and at least one of the people who did this was part of the ACM programming team. So we had multiple people try to program the best possible priority queue prim they can. Oh, I just got a swirl that I got a little lag there. So we've had people program the best possible prim priority queue version they can for a sparse graph, and their first shot at Kruskal ends up faster than their fastest prims. I think it's part of it is Kruskal just makes better use of the cache than prims does. And so if you had a sparse graph, I would always go with Kruskal. Downside is you've got to implement union find, but the upside is it's the fastest. Now, when you get to project 4 part A, what you need to decide is that graph sparse or is it dense? There's only one answer. You don't have to implement both. You've got to look at, is this graph going to be sparse? Is it going to be dense? And what you should do is look at different situations. What if they were all in the lab? What if they were all outside of the lab? What if it was half and half, with one obviously would have to be in the quarantine for it to be possible? In those 3 cases, would you consider them dense or sparse? And then that'll tell you which algorithm you need to implement. Okay, last thing. Prove that Kruskal always finds an MST. Not just that it finds a spanning tree, but that it's minimum. Prove that prim always finds an MST. Prove that prim could start at any vertex, and it might find a different MST if you start at a different vertex, but it would find an MST. And if you want to do these, it's not critical. Doing these will not make you better prepared for the final, but it's good things to understand about the algorithm. Just think about this one. How can you prove that prim will never produce a cycle? We looked at how Kruskal never produces a cycle. How does prim prevent cycles? It doesn't use union find. What method does it use to prevent cycles? And the in-class MST quiz and the proof by contradiction would help if you want to do these. Okay, that's it for today. Let's get done. Let's get some lunch, and we'll see you at office hours.